live in the Faroe Islands, where I work for language technology specifically for the Faroese language. But I decided it was time for me to branch out and investigate new languages and the new linguistic systems, and especially in order to find, common strategies that work for everybody. And this is the reason why we're now today looking at Catalan and its relatives and the Romance dialectal continuum, and we will see in a second what that is. But basically, what we're looking into today is is it moving? Yes. So in terms of in the context of speech recognition, if there are any strategies that we can look into that allow us to choose what is a good language, similar language that you can use in order to optimize transfer learning. So we're looking at the context of low resource languages, so languages that by themselves don't have enough resources, and we're asking, okay, I need to use another language in order to boost performance for this specific task. What language do I choose? Basically, this is the question that we're trying to explore today. So basically, we're going to look into what cross-lingual learning is. Probably you all are already familiar, but this was supposed to be, for approachable for everyone. So we're going to look into that for a little sec. Then we're going to talk about language similarity and what we actually define as language similarity. We're going to look, at previous approaches that people have used in order to select auxiliary languages. So these languages that we use in order to optimize transfer learning. We're going to look at Catalan and the dialectal continuum. And specifically, we're going to look at these languages from the dialectal continuum, how they're represented within models, and if these representations can give us a clue about what languages are similar and what languages we should use to optimize transfer learning. And finally, we're going to summarize on what insights we can gain from this and what are our working hypotheses for the time being. So first of all, we're talking about low resource languages. What do we mean by low resource languages? Well, we basically mean, this term is used very loosely typically, but it can indicate literally any language that is not English. So basically any language that by itself does not own all of that amount of data that we can use in order to train model optimally. And this is true for English. And the situation can get much, much worse depending on what type of languages we look at. So this is like the percentages of NLP solution by language. 67% are about English, and the rest of the languages need to share whatever is left of it. So low resource can mean many different things. It can mean that we don't have enough data to train the models, but it can also mean that we don't have monetary resources to train the models. We don't have computational infrastructure. We don't have a socioeconomic system that allows for these sort of things. Because if you look, for example, at the languages in Asia, they have plenty of native speakers, billions, and still they are low resource languages because it's not being invested in those languages yet. On the other hand, we also have languages that are very, very small number of speakers, like, for example, Faroese, that have 75,000 speakers. That is also low resource, mostly because there aren't much data, but they make some investment because they are in a rich country in the West. So basically, low resource can mean many, many different things. But in general, one of the strategies that is used in order to tackle this lack of resources is to use transfer learning. So just a little summary of what are internal representations inside models. Of course, we typically see the language model or the speech model or whatever we want to call it as a black box. We put in an input and we get an output out of it. But of course, these models are typically made of different layers, and all of these layers output an intermediate representation of the input. And these intermediate representations are actually very rich in terms of information, but they're not directly interpretable by humans. What we know about these representations for the time being is that typically they represent information in a hierarchical way, starting by low-level features at the low layers. So, for example, for a language model, it can be the syntax, the morphology, and other aspects of the language. While in the higher layer, we have more like the semantic information. So basically the meaning of what we're talking about. So basically, this is what we know, and this is what we're gonna also be looking into later on. But these internal representations have also quite some interesting features that we can exploit. One of these is that if you take languages, different languages, and you train them together in these models, they will end up, even without constraints, in creating internal representations that are similar for similar languages. So you will see typically languages from the same family clustering together inside the layers of these models, which is great because it means basically that we can use the representation of a similar language to adapt to our task language, our low resource language. And this process is called cross-lingual transfer typically. So basically, we take a higher resource language that is similar or related. We hope that the internal representations, the syntactic, the morphological, and so on information that is encoded by the model will be similar. So we only have to the little step of adapting this representation rather than training from scratch. Now, transfer learning is used basically, or cross-lingual transfer is used basically in most contexts nowadays, and it is a key strategy for tackling the lack of resources in low-resource languages. However, there are some issues, there are some caveats that we need to keep in mind. So it's not a given that a language that works well for one task will work well also for another task. So basically, the choice in language can be task specific. And on top of that, we don't know a priori, we don't know beforehand what language will work well for whatever task. And what is typically done is either to rely on intuition. You can hear native speakers, like for example, Faroese. I hear people say like, "Oh, Norwegian sounds just like Faroese. I can use Norwegian." Or like, "Oh, Icelandic has the same conjugations as Faroese. That's perfect, right?" This is all true, but like, what do we even talk about when we talk about language similarity? So we're also gonna look into that soon. Typically, what people do is to try out different models with different languages, right? We train with different languages and we say, okay, it works best with this one. Or better yet, if you have the computational resources to do it, just put everything together and just train with multiple languages. However, not everybody around the world has a Mare Nostrum lying in their basement. And these processes are typically very computationally expensive. Think about, for example, the people that don't have GPUs in-house, and maybe they have to rely on cloud services. Trying out 4 different models and starting out without knowing beforehand what languages will work best means that you're going to have to spend 4 times more, 5 times more, and so on. So, as I said before, low resource is not just a matter of amount of data, it's also a matter of amount of computational resources. And moreover, trying out different languages means also that you have to collect the data from all of these languages. And maybe have people that are kind of proficient in these languages that can confirm like, yes, this is actually my language, this is not gibberish. So I hope I convinced you that it is good to have an idea beforehand of where one should try, what languages one should try rather than proceeding blindly. Typically people just look for languages that belong to the same language family, because that's a good intuition. I'm just going to pick something that is kind of related to my language.
Sorry, when you talk about task languages, you're talking about the projected language, the target language.
Yes, yeah. Yes, sorry. So let's look now into language similarity and what we mean when we talk about language similarity. What do we mean when we say that a language is similar to another one? This can happen in many different ways, actually. This is a nice map that I found with lexical distances. I think lexical distances can be a good reference for what people mean typically by similar language. Oh yeah, you say, I don't know, you say cosa in Spanish, we say cosa in Italian. We have a sharing root there, right? So this is what we mean by typically lexical overlap, and that can be measurable, with vocabularies. But that is only one way to look at how similar two languages are. Another example can be the syntactic similarity. So is it the same word order, for example? But also in general grammatical constructions. One can look into morphological similarity. This is for example, the case of Icelandic and Faroese. They will have endings that are inflected more or less in the same way. So these are like suffixes, affixes, conjugations, and so on. Then we have the phonological distance, the phonological similarity, that is basically similarity in pronunciation. But not just that, it's also prosody and stresses, accents, and so on. Then again, we can look at it from an orthographic point of view, the scripting. Are we writing in the Western alphabet, English, Italian, and so on, or are we writing in with Japanese kanji and so on? That actually makes a big difference in how much transfer learning you can have. And then finally, we can also look at it from the typological point of view, which are more like higher level features, like gender system cases and what sorts of verb tenses we have. So basically, all of this is language similarity. Do you want to take a guess on which ones of these matters more for speech recognition? I mean, I think one could guess that probably sound will play a role in it, but we're gonna look into that more now. So our research question right now is, okay, of these dimensions, are there any that matters more when it comes to speech recognition? And when it comes to that, should we rely on theoretical linguistics classifications, made by linguists, rule-based? Or should we rely on a data-driven approach? Should we analyze the data sets? Should we analyze the models? Should we analyze the representations? So we're going to look into these two different approaches and see which one can actually inform us better, if any, or a combination of the two. And another question could be, okay, what about the closest relative to our target language? Is it the one that is guaranteed to have the best transfer learning or not? So we're going to look into that. Just, a quick summary of previous approaches that people have taken, especially in terms of quantifying language similarity. This is the Uriel knowledge base, which is basically a database that collects theoretical information about languages by aggregating it from different data sources. And thanks to this information, it creates vectors that basically encode different features of that language. And once they're encoded into vectors, it's very handy because we can do mathematical operations on them. So Uriel divides into typology, genetic, and geographical information. And then the typological one can also be split into syntactic, phonological, and inventory, that is basically phonemic inventory. So basically the dictionary of phonemes that are present in a language. So cool. So basically these people have already aggregated the data for us. So maybe we can look into them and look at these vectors. And thanks to these vectors, you can actually calculate distances between languages. Of course, this is completely rule-based, right? So it will not take into account variations in data sets, for example, and it will not take into account how different models can perceive language similarity. But this specific database has been used a lot to study cross-lingual transfer, among other tasks. And it has been also quite influential, considering the number of citations that came out of it, despite it has some serious limitations, like, for example, that many of the lower resource language have missing features, and the results are not always reliable in these cases. But basically, people have used that in order to study transfer learning and to predict also this problem of auxiliary language selection. This was one specific paper that I like to point out because it's really relevant. These people basically created an algorithm based on a decision trees that would allow us to rank languages in order of better cross-lingual transfer. So basically they trained models, and based on the results, they trained this ranker of languages. And they did it for 4 different tasks. So machine translation, entity linking, part of speech tagging, and dependency parsing. Now you will notice that these are all text-based tasks. So there is nothing quite similar to it for speech recognition, to my knowledge yet. Yeah, basically what they found is that they could reasonably predict, which languages would work better for cross-lingual transfer in these tasks. And thanks to the fact that they used a tree-based structure, they could actually look into the tree and see which features mattered most for different tasks. So, for example, they found that for machine translation, the word overlap in the data sets and the subword overlap were the most meaningful. So this concept of lexical similarity, right? So you have these data sets of the target language and the auxiliary language that share very much pieces of words. This helps the most, together also with the size of the data set that goes a little bit without saying. But for other tasks, like for example, dependency parsing, then syntactic similarity extracted from the URL vectors, that was the best predictor. And they also mention in the paper that doing this for every system of languages, of training models and then training a predictor, is unrealistic. We cannot really do it. But thanks to this process of doing it for a few case studies, you can actually get to the best feature to predict and make educated guesses on what language will work best. So yeah, but these were all text tasks. Speech recognition is a little bit more complicated. And it's a little bit more complicated because it's not just about, lexical similarity, syntax, and morphology, and so on. I mean, these things still play a part, but you have the whole thing of pronunciation, prosody, phonetic variation, and in general, a complex mapping from sounds to words. You also don't have like fixed discrete units like tokens that you can look into, right? Because it's all a matter of how do you discretize audio. So speech recognition is particularly complicated on this particular task. However, there's been people who have looked into the models, looked into the layers, and seen that indeed different type of information is encoded in different layers. This is particularly a study on Wave to Web 2, where they identified, that yes, there are local features, local acoustic features that matter, and they're particularly expressed in the first few layers. Then you have phone identity that has, is expressed also very much in the first part of the model, less so towards the end. But you also have word identity and word meaning, so this part of semantics. So this, I think, gives a very good idea of why guessing the best language for speech recognition is particularly complicated. Because not only you have all of these things that you have in the language models, but you also have the acoustic features to keep into account. And this, after this very long introduction about language similarity and what we're looking into, brings us to our case study for today. Our case study is basically on Catalan and its relatives, and we asked ourselves, okay, can we look into these URL vectors? Can we look into model representations? Can we look into the data sets and actually guess which one of the relatives of Catalan will work best in boosting Catalan speech recognition? Now, I built quite a suspense, so I hope I don't disappoint you at the end. Yeah.
Sorry to interrupt. Speech recognition, but I know that for textual comparisons, attempts at attributing a similarity between languages, what people use normally is for the sake of simplicity, is some sort of a standard version of a given language. So they want to. The difficulty is in defining what standard means, right?
Yeah.
They want to compare standard English with standard German,
Yeah.
and so on. They don't want, I don't know, Sächsisch from northeast Germany to be compared to some dialect of Italian down south. Does the same exist? Does the same drive toward representing speech by standard speech exists? Is there this preoccupation among ASR?
I mean, I think from the point of view of speech recognition, you want to make sure that you give equal representation to all, and that of all the variants, right? And that your model is robust towards the sort of variations. So I guess it depends on whether you want to try classification, and in that case you need a standard, or if your goal is maximizing the performance of speech recognizer. Because if you're trying to maximize the performance of a speech recognizer, you cannot base yourself just on a standard variant. So.
But do you have a way when you do ASR to actually build a synthetic version of a standard speech in a given language? Do you have, is that feasible? Is that a thing, or is it just not?
I think for that you can ask this guy here who is trying to do speech synthesis for different dialects. Is probably the best person to answer about, because ASR just needs to recognize. But if you actually want to reproduce a certain speech, then probably he's the best person to answer. All right. Okay, so let's look at our system and what we're studying right now. So this is the Western Romance dialectal continuum. A dialectal continuum is basically a system of languages where languages are not clearly separated one from the other, but rather we see a gradual variation from geographical areas. So if you start walking from northern Italy and you get all the way here, passing through the south of France, you will notice that language changes gradually. And it gradually morphs from, Lombard, Piedmontese, Ligurian, these are the languages of northern Italy, all the way to Catalan. So these are the genetic or phylogenetic classifications. Here we find Catalan. Its closest relative is Occitan, of the languages of this study. Then we see Spanish here. Here we find French. And here, again, in the Western Romance, we find the languages of northern Italy, Gallo-Italian. If we leave the Western Romance, we can find the South Romance, where we have Tuscan, which is basically a fancy way to say Italian. So here in purple is Italian. And then we can find the Balkan Romance, that's Romanian, all the way over to the east. So basically, this is the system that we're looking into. So I have, as I mentioned before, used the Uriel vectors in order to measure the distance between some of these languages. So here, what you find represented here are the distance between Catalan and these specific languages. We find Occitan, the closest relative. We find indeed that its genetic distance is the smallest. That's because we're looking at the closer language from a genetic point of view. We find Occitan and Spanish be the closest geographically. This makes complete sense. The closest genetically as well. From the point of view of the phonetic inventory, unfortunately, I did not have enough features for Occitan, so we don't have that type of information. But we find, interestingly, that the closest relative from a phonetic point of view is Italian, which was not even in the family of the Western Romance dialects or languages. So this is an interesting fact, and I want you to put it in your pocket for later. So we find Italian and French being the closest ones from a phonetic inventory point of view. From a syntactic point of view, we find Occitan and Spanish being closest, and featural is basically the typology part, so basically verb system, gender system, and so on, where we find, once again, Occitan being closest, with Italian in a close second. Great, so this is basically what we find from a purely theoretical point of view. So now, what we're going to do is to take this information, put it on one side, and now we look at the models, both text models and speech models. We open them and we look at the inner layers, and we see how these languages are represented inside them. The datasets that we're going to use for it are Flores 200 and FLIRS. Have you ever heard of these datasets? Flores is very much used in machine translation. This is a benchmark that was created in machine translation and contains 200 languages. Basically, it's the same sentences translated in 200 languages. They are originally English, which sometimes creates some issues because there's like stuff about Biden or whatever, and you're like, okay, this is not particularly relevant to my Faroese life, but fine. So, but the good thing for this particular study is that these are the same sentences, which is good for us because, as we've seen before, in the models we also encode semantic information, so high-level information, word meaning, which is not strictly relevant in our case, right? Because we only want to look at the characteristics of the language, not at what has been said. FLIRS is also really interesting because it's basically the spoken version of Flores. So basically, it's speakers that read aloud the Flores sentences. Now, this is really cool. Unfortunately, this only covers 100 languages of the 200 of Flores 200. So maybe in the future there will be an extension, but for the time being, this is what we have. Then we also use some non-parallel dataset. Non-parallel means that it does not contain the same sentences, and we mostly do this to check what happens, to explore what is the effect of having the same dataset or not. And for that, we use Common Voice for the languages in our study, but this particular dataset for Occitan, because we didn't find many hours of, unfortunately, Occitan in Common Voice, this dataset that is compiled by the Permanent Congress of the Occitan language. So this would be the languages of our study. Italian, I included 2 languages of Northern Italy, that's Lombard and Ligurian, Occitan, French, Catalan, and Spanish. They are all covered by Flores 200. Unfortunately, the 2 languages from Northern Italy are not covered by FLIRS, so we are excluding that from audio essay, and they're also not represented in Common Voice. But basically, for the speech part of the analysis, we're going to have Spanish, Catalan, French, Occitan, and Italian. Unfortunately, some of the languages of this study are low resource, which means that they're not good candidates for cross-lingual transfer, because we would like, in theory, to pick languages that have more resources than the one that we're looking at from target language. But it is what it is. Basically, here we want to study language similarity and how it impacts the model. So for the time being, we're going to roll also with low resource languages. And we're also going to find something interesting about that. But again, I don't want to create too much, tension. We're going to see it later. These are the models of our study. We're taking 1 text model for reference, and then 3, that's BERT, and then 3 speech models, UBERT, Wave2Back2, and Whisper. So these models are different. They're very often trained with different objectives and have different architecture. What they all share is that they all have a transformer encoder. Either they're made of a transformer encoder, or they also contain a transformer encoder. And basically, this is the part we're going to focus. So basically, we look at how these models encode the languages, and we do so by extracting the representations from the transformer encoder. So this is the workflow. If the equations make you uncomfortable, close your eyes. I'm gonna be quickly just explaining what this means. Basically, we run our sentences through the model. We don't really care about the final output, so we forget about it for the time being. And then from each layer, we extract the representation of that specific sentence in that specific model. We're gonna, of course, one sentence is made of different tokens or audio features. If it's a speech model, we're gonna be averaging over those so that we have just one representation for one sample or one sentence. And then once we have that, we basically compare sentence by sentence via cosine similarity. So basically, I have a sentence that says, hello, my name is Barbara, and one that says, hola, me llamo Barbara. These are the same sentence. I take the representation and I compare them by cosine similarity. And then finally, I just average over all the cosine similarities over all the sentences that I have. And this is for parallel datasets. For non-parallel datasets, basically, we just average all the representation over one language, because it wouldn't make sense to compare one language, one sentence to one in another language that means something completely different. But basically, the pipeline is the same. It just changes when we are averaging so that we get just one identifier. So let's look at what we find, basically, by extracting this representation and ranking them in the models. This is from the BERT models. We have English BERT and multilingual BERT. And here are our languages from our study, ranked based on which one is the closest to Catalan. So we find, for example, that Occitan in English BERT is reliably the closest to Catalan over all the layers. And this is an interesting information because, as we've seen previously, Occitan, from a genetic point of view, syntactic point of view, and many others, geographical and so on, is the closest to Catalan. So this is a proof, that this makes sense. We find Occitan is first, and we find the German. Oh yeah, I added German for sanity, which sometimes it can be surprising that German is same. Surprising, but yes. German is reliably last, which makes sense because it's the relative that is, well, it's not related as a Romance language, but it is a Indo-European language. So it's the one that is further off with respect to Catalan. We find that Spanish is second, and then we find the two languages from Northern Italy. So basically we see this dialectal continuum. Then we see French, finally Italian. So basically what we saw before with the map of the genetic relation, we find it completely or more or less represented inside English BERT, which is cool because it tells us that indeed this internal representation are informative in terms of linguistic similarity, at least in this case. Then we will see that things get a little bit weird further on. If we compare it with multilingual BERT, we see actually something very, very interesting. First of all, this overall similarities increase. So you see a lot of red here. One second. I need to. See that the similarities overall increase. And that's because we have that multilingual training that pushes the representation together, right? They tend to align representation for different languages. So they push them closer together. This means that everything will look closer, which is great. But we actually start seeing things get a little bit strange. So Occitan starts out well as first, but then it has a drop in the higher layers and goes to fourth. At the same time, Ligurian and Italian that were very high up. Here they were third and fourth, more or less. Suddenly they're the last languages of our study, even worse than German. So, and the other rankings are more or less respected. So what are we actually seeing here? So I can only give you my guess. So my guess is that multilingual BERT has seen quite a few languages. It has pushed the representations of these languages together, But this is not necessarily true for the languages it has never seen before. Like, for example, Occitan, Lombard, and Ligurian, because these are the low resource languages. So it has never seen them. It has not pushed the representations closer together, so it perceives them as further off. So this is already an interesting information that we need in order to interpret what we see afterwards. It's not just a matter of what languages are closer, it also matters what is the data distribution that the model has seen, right? So we have these two things that we need to keep into account. I also checked the lexical overlap between the Flores text data. Basically, I'm looking into the shared tokens between these Flores sentences with both the verb tokenizer and the multilingual verb tokenizer. And here what we find is basically what we would expect from the dialectal continuum. First is Occitan, then Spanish. Lombard, French, and Ligurian are more or less in between. Last is Italian, that is the further away relative, and then finally German. So this is not surprising. This is what we would expect. In fact, there's been also a study that has shown that these multilingual verb representations can be aligned to URL vectors. So it's not surprising that we actually find that there is a correspondence between the genetic information, what we know beforehand, with the verb representations. However, this might not be the case for speech models. So let's look into those. So since we've seen that models trained with English and models trained with multilingual strategies, so different languages, can yield different results, I'm separating them for the rest of the analysis. So what I find with Wave2Vec2 base English, so that's the first speech model we're looking into, is that Occitan is reliably last. And very much so in both English and multilingual Wave2Vec2. So we go from first, from the point of view of textual similarity, to the last one from the point of view of the speech models. We found.
Sorry, when you say last or first, do you base with the ranking you mentioned on the last layer or on the average of all layers?
Yes, I'm averaging them mentally, but because this is a fifth, there's always fifth, so I can say that this is reliably last, and the same goes here. Yeah, in the higher layers we see like something changes, but again, we're mostly focused on the early layers because that's where we find the more low-level language-dependent similarity, right? As we've seen before, like in the distribution. However, later on, I showed the ensemble for all the ranges of layers. So right now, we just look at it qualitatively, and then last we see the ensemble ranking for early, middle, and late layers. So we see that there is a difference actually. Overall, though, we find that Occitan tends to be last. Italian in the English one tends to be first. It is also first in the early layers in the multilingual Wave2Vec2. We actually find that German scores closer to Catalan than Occitan does for the most part. So yes, we see that the picture is starting to change. This is the case very much also with Hubert. So with Hubert, I didn't find a purely multilingual version. So I'm separating the one trained with English to the one trained only with Catalan that was trained here at BSc. So here what we find is early layers, Italian is first, Occitan is always last, again. It changes a little bit in terms of Catalan Hubert, where in the very, very first layers and in the last, Occitan is suddenly first. So this gives us a clue that actually it has to do very much with there is big change that depends on the data distribution of the model. So it is not enough to just look at theoretical information about the language. Yes. For Whisper, we find that overall the similarity is much, much higher. I think that's because it's trained with a different objective with respect to the other models that we looked at so far. So this is also meant for speech recognition directly, but also for machine translation, which means that it will push language representations together because it needs to translate from one language to the other. However, the overall trend that we observe is very similar to before. Occitan tends to be last in most layers for both the English version and the multilingual version. Spanish tends to be first, sometimes exchanging place with Italian. And yes, there's a lot of variation, but this is more or less what we observe. So now here are the ensemble rankings. So we divide the early layers, middle layers, and late layers. We see that in the early layers, the ensemble ranking between the models for the English models is typically Italian first and Occitan last, with Spanish being a close second, while for the middle layers and the late layers, Spanish and Italian flip, and basically Spanish tends to be first. This is not entirely surprising if we think about what we've seen before, where basically in the middle layers and late layers, we see that word meaning and word identity have the lion's share, basically, the type of information that is conveyed. So basically, we get that the lexical similarity between Spanish and Catalan is probably very, very high, just because they're just spoken in the same place, right? So this is not completely surprising. What, to me, is rather surprising is that Occitan, more or less, is always last in this ensemble. So closest to genetic relative, but last. Possibly because of the data distribution inside the models. Of course, these technically should be all English models. However, these big models, they're trained on massive data sets. They're almost always not 100% monolingual. So if I had to guess, I would say that there was probably some Spanish in it as well. I mean, this is a fair guess to have. The situation is very similar for multilingual models, where we find Italian first in the early layers, Occitan is always last, and Spanish is first in middle and late layers. And this was done on FLIRs, right? This was done on parallel data. However, no data set is perfect. And it was flagged that there are a number of incorrect audio samples in FLIRs. So FLIRs is really cool because we have these parallel sentences that allow us to compare and so on. However, it would be good to have another data set of this sort to compare with, right? Because there will be some features that are data set dependent. However, we don't have, parallel multilingual speech data sets that grow on trees, so we're going to have to do without, basically. So we relax the constraint on parallel data to see what type of results we get. So this was on common voice and on the Occitan data set that was provided by the Congrés de la Lengua Catalana, Occitana. We find that there is some reshuffling in the early layers, with French now being first and Italian being last, for being second to last for some reason, and then Occitan reliably always last. All the models agree, literally. Spanish is first in middle and late layers. Multilingual models, they absolutely all agree. We see that the ranking is the same, basically, except for maybe later layers. Late layers, we find German, but Occitan is close to last. Occitan is last in both middle layers and early layers, and first is Spanish always. So now we know what the models think. The question that we have to ask ourselves now is, okay, but then what happens if I train Catalan together with these other languages? What if I try this multilingual training and see which one works best? What are we going to see? So we did that both with the FLIRs dataset and with the Common Voice dataset. And we tried training on a small number of hours, 10 to 15 in both experiments. And basically, quite unsurprisingly, we find that in both cases, Catalan and Occitan, the model trained on Catalan and Occitan, performs the worst on both datasets. And on the other hand, we find for the first model, the one trained on first, Catalan and Italian having the best word error rate, and for the second one, Catalan and French having the best word error rate. So now, across all of this exploration, I've asked you to put some information in your pocket, so we're going to take it out now and see if you actually remember it. We had seen back in the URL vectors, the one phonetic information we had was about phonetic inventory. And the first two languages in terms of phonetic inventory were Italian and French. So the ones that we see perform the best here. So that is a clue. The other clue is that inside the models trained with English, we found for the first data set in the early layers, Italian was first. And in the second data set, French was first. So basically, we start seeing some guesses. So my guesses right now would be, first of all, that there is some dependency on the data set. So while for one, Italian performs best, for the other, French performs best, this is not surprising at all. Of course, whatever we train is going to be highly dependent on the quality and the type of data that we feed it. So of course, we cannot find, the best answer for all of our problems just out of the box. Secondly, it looks like phonetic inventory is informative, and it looks like information in the early layers of the model is also important. Because afterwards, it's always Spanish being the closest one, but in the early layers where we have the local acoustic features being processed, that's Italian and French performing better. So basically, if I had to, right now, decide what directions to take, I would say, okay, before training your model, just take a subset of the data set, run it through the model, and see what happens in the early layers. Which are, again, the layers that process the low-level information. And maybe even look before those at the convolutional layers, maybe the ones that really, process the raw audio and find the features. And lastly, I think the most interesting result of this initial exploration is that Occitan, despite being the closest relative, despite having the highest lexical overlap, despite having the highest syntactic similarity and so on, is the one that reliably performs worst. And my guess is, I don't know about its phonetics, I'm just looking at it from a purely data-driven perspective. My guess could be, it's a low-resource language, probably these models have never seen it, they will perceive it as further away because it was not embedded in how the models were trained and how this multilingual space was created. So this is actually, and this is a fun fact, we're doing a similar study for Faroese and its relatives because the dialectal continuum is something that is also in the Scandinavian languages. And we find that the Icelandic, which is the closest phylogenetic relative, the closest syntax and so on, is the one that performs the worst. So my guess so far would be, do not trust genetic ties. Do not trust your family. Do not trust your closest relatives. So basically, choosing the closest phylogenetic relative is not necessarily a good guess. So basically, these are the results from this month. Basically, it's basically just the beginning of this exploration. However, we can try to draw some working hypothesis for how this study is going to move forward. So basically, the hypothesis is to not go for phylogenetic ties necessarily. Do not go necessarily for low resource languages because even though they're very similar, they will not perform well on top of not having, big data sets to access with. And then look at the early layers and the phonetic inventory of the languages you're interested in. It could be interesting to write heuristics that take into account the characteristics of the model and the characteristics of the language in terms of phonetic inventory, and try to see if you can make like some sort of predictive ranker, basically, of what languages work better in ASR. But of course, these results will only be valuable if they can be reproduced in different language families. So for the time being, we can only take this working hypothesis and test them in other language families as well. This was all. I hope I answered some of your questions and not just created more of them. But if you have some, please ask me.